Hello everyone, this is Mr. Younger again. I'm here to solve a radiation problem, and let me begin by sharing my iPad screen. All right, so my iPad screen is now being shared with you all, and I'll read the problem to you. It says a person sitting in an empty gym is radiating their body heat out into the gym. Additionally, they are absorbing heat from the air that surrounds him in the gym. Assume the person's temperature is 34.0 degrees Celsius, the air temperature is about 18.0 degrees Celsius, and the person's surface area, minus the part touching the wood seat, is about 1.6 square meters, and that their emissivity is 0.73, and use that data to estimate the person's total heat loss per second. Obviously, that's a huge run-on sentence, but let's just ignore that and solve the physics problem. We often estimate in the physics world that the average human puts out about 100 watts every second in a normal room temperature room, and that's why when you walk into a gym that might be quite cold and empty, after a few hundred people get in there, it actually gets quite warm. So that's partly what we're showing here. So let's start off with the solution. What we're going to use is the Stefan-Boltzmann equation, which basically says the heat added per unit time, Q over T, is equal to an emissivity, that's that little epsilon there, which is a measure of what fraction of the heat they can actually emit. It's a number that goes between 0 and 1. The closer you are, or the thing is, to a black body, the closer the emissivity gets to 1, and the closer the thing is to a pure white uh, object that actually reflects all of the energy as opposed to absorbing any, then the emissivity gets closer and closer to 0. There is a Stefan-Boltzmann constant, sigma, which is 5.670 times 10 to the negative eighth watts per square meter per Kelvin to the fourth. And then in addition to that, there is a surface area of the object times the temperature 1 to the fourth power minus the temperature 2 to the fourth power. And what this is the realization that in reality, every human being or everything with a temperature greater than 0 Kelvin, which is essentially everything, everything with a temperature greater than 0 Kelvin will both radiate and absorb heat. They will radiate it at what I called in this equation temperature T1, and the surroundings, if they happen to be temperature T2, the person will, or the object will actually absorb the amount of heat using the same equation, but using temperature T2. As I said, the Stefan-Boltzmann constant is 5.670 times 10 to the negative eighth, and that's watts, which remember is a joule per second, per square meter per Kelvin to the fourth. So you, of course, have to make sure you use the temperature in Kelvin as opposed to Celsius, just like the ideal gas law. Additionally, you have to use the area in square meters, just like, well, like a lot of ways we prefer when we're using the ideal gas law, but you can actually use, if you use the right R value, you can use different constants for that. So let's go ahead and begin. According to the Stefan-Boltzmann law, the amount of heat Q emitted, and this is actually total because we're actually taking the heat radiated minus the heat absorbed. So this is the total heat radiated. Q over T is equal to the emissivity, which we were told to assume at 0.73. The area, that means the surface area of the object that's actually doing the emitting and absorbing. And in this case, the average human body tends to be around 2 square meters in surface area. That's often what we use. We've subtracted a little bit to make up for the fact that their butt and back legs are probably touching the bleachers. So we're going to put 1.6 square meters for that. I got it out of order, so I need to go ahead and put in the Stefan-Boltzmann constant as well, which is 5.670 times 10 to the negative eighth. And that again is watts per square meter Kelvin to the fourth. So notice, yes, I am using the equation, but I ended up writing epsilon and then A instead of epsilon sigma then A. So now I have the temperature T1 to the fourth, and that's supposed to be the temperature that they're radiating at, and that is characteristic of the person's body temperature, which is 34 degrees Celsius. If we convert that to Kelvin, that's 273 plus 34, so that should be 303 plus 4, that'd be 307 or 307 Kelvin. And that's to the fourth power, minus the other one is 18 degrees Celsius. 273 plus 18 is 283 plus 8, which would be 291. So this is 291 Kelvin to the fourth. Double checking my arithmetic there just because I often am doing arithmetic on the fly. It's very easy to make a careless mistake. So I'll say 34 plus 273 is equal to 307 and 18 plus 273 is equal to 291. So that works just fine. Now I take 0.73, I multiply that by 1.6, I multiply that by 5.670 times 10 to the negative eighth, and then I multiply that by parentheses 307 to the fourth power, and then I have to slip back down. My calculator automatically assumes you're still in the exponent for a little while. So now I'm going to do 307 to the fourth power minus 291 to the fourth power, close parentheses. Again, my calculator assumed that I still want it to be in the exponent, so I had to stop again. And this gives me an answer of 113.4 watts. So I had suggested in the prologue to talking about this that it was the average human puts out about as much as a 100-watt light bulb. In this case, we're getting around 110 watts. So that is somewhat consistent with what I claimed, and it should be somewhat consistent with what you can use for day in and day out regarding a human in the presence of a room temperature room. So I hope that was pretty straightforward and understandable to you. The emissivity, like I said, is much closer to one when the object is black and becomes therefore a perfect emitter and a perfect absorber. And when it gets closer and closer to zero, it's more like a white body, and that should, in principle, emit or absorb zero heat. So other than that, we are done. I hope that helps. Thanks and have a good day.